Perfect.
Yeah, apologies everyone. Hope you can all see the presentation now. NanoInsulate's a project that's now been going on a number of years. It actually started in July 2010 and will be complete in July 2014. And as a result of that, we have a number of achievements for the project, which I'll go through, and still a number of objectives which we hope to complete by July next year. Now, the purpose of the project is to produce high-performance opaque and transparent insulation for energy-efficient buildings. So it's primarily targeted at construction, and it's primarily around vacuum insulation panels and microporous cores. Now, immediately we target construction. We come across a problem with vacuum insulation panels, which is that they tend to be vulnerable. They're ideal for application in controlled temperature transport, in refrigeration, where there's a relatively controlled manufacturing process. And in both those applications, certainly in controlled temperature transport, the lifetime requirements are relatively short, normally only a few months or maximum a year. And in refrigeration, the lifetime expectation is probably in the order of 10 to 20 years. For construction applications, you're really looking at lifetimes in excess of 25 years, and our target is certainly 60 years plus to cover both domestic and commercial buildings. So the partners involved in the project, we have, I think it's 9 partners. We have Kingspan R&D from Ireland, MATI, which is an offshoot of PERA, Polymer Engineering Research Association, based in the UK, Hanita Coatings from Israel, Vacutech in Germany, Fraunhofer in Germany, two parts of Fraunhofer involved, Koç University from Turkey, Airglass from Sweden, BASF from Germany, Fundación Geica from Spain, and Acciona, also from Spain. So getting on to the results we've achieved so far, we have novel nano-structured translucent Cirrogel composites with polymer PDMS synthesized by a new deposition technique, and that really is a result of work done by Koç University. We then have a novel silica-based aerogels synthesized in moderate size for aerogel panels, and you can see an example of one down here. It's 500 by 500 millimeters, I should say, not centimeters, by 15 millimeters for transparent VIP production, produced by Aeroglass, using the technology coming out of Koç in partnership with Koç. And then for the opaque panels, we have new open porous monolithic materials developed. And here, quite excitingly, we've actually got an initial thermal conductivity down to 3.6 milliwatts per meter Kelvin, which is of the order that we commonly see with fumed silica. So that is a very interesting achievement for an alternative core. This will help to achieve the third objective. We obviously have robustness and lifetime as one objective. The second objective is performance of the VIPs, and the third objective is to achieve a low-cost production, which is necessary really to get widespread use in the construction industry. High barrier films have been developed where the gas vapor transmission is less than 5 times 10 to the minus 3. And this is developed between Fraunhofer and Hanita Coatings. And the importance of that is obviously increasing the lifetime of the product. If you have very low vapor and gas transmission, then you obviously can increase, based on the curve that Daniel showed earlier, you can increase the lifetime of these products quite dramatically. And we have a laminate of the structure, polyethylene terephthalate, metallized film, lacquer, aluminium layer, adhesive, LDPE, with very low water vapor transmission rates. That's also between Fraunhofer and Hanita. We have, during the course of the project, developed lifetime test procedures for VIP type approval and durability testing during the lifetime. We've got new technology for measuring permeation rates, and we've got life cycle and end-of-life assessments of these novel materials developed through GEICA. We have initial designs. Obviously, one of the important things in developing VIPs for construction applications is in terms of the robustness of the uses we've talked about, but also developing systems that ensure there is no damage during installation. And that's been concentrated on in terms of the installation of rain-screen cladding systems, floors, roofs, cavity and external wall insulation by Kingspan, and also design and specification of a VIP production line for a continuous cost-effective VIP manufacturing route, again targeted at reducing the cost of manufacture. We have demonstration sites for part of the nanocluster that Inati mentioned earlier at Algete in Spain, which has now been going for over a year, and at Warsaw in Poland, which is just starting up to ensure that we get the true effects of a decent Polish winter. The completion objectives for the project in month 28 are super low barrier to water and air films enabling low long-term thermal conductivity for a lifetime, as mentioned, of greater than 60 years, and targeting a declared lambda of 6 milliwatts per meter Kelvin for opaque VIPs for building applications. A nanofoam core that achieves the same lambda value as fumed silica-based core with lower long-term cost and improved life cycle analysis values, and also obviously achieving the long lifetime that you currently see with fumed silica cores. Aerogel-based core for the transparent VIPs with improved handleability, more robustness, durability, and good transparency suitable for building applications, and that's quite a challenge to get both reduced friability and maintain good transparency. And application technology to enable the widespread use of VIPs in building applications for floors, walls, and roofs without losses due to mishandling and puncturing. And an overall lower cost production unit per unit value, unit R value of the VIP to enable non-niche, more widespread use of VIPs in construction. Okay, and thank you very much for listening.